So now we need to go further with the controller design, as we saw in buck converter's case, that how the controller is actually designed to run this boost converter, which decides the switching frequency or when to switch on or switch off these switches. And at the same time, this operation has to be stable. All this is discussed in buck converter's case. So similar concept applies for the boost converter's phase. So now, concerned about the losses in boost converter. So ideally, losses are negligible or equal to zero in these switch mode converters or switching regulators. So in this case, again, this switch over here, S1 NMOS. So S1 is designed using NMOS switch, N-type MOSFET, and S2 is designed using PMOS, P-type MOSFET. And this controller over here decides the switching on and off of both of these switches after getting feedback from the output voltage. But until now, we haven't discussed about these PMOS switch. We were talking about switch S1, which is NMOS, and diode D1. This PMOS switch is normally used in industry or in practical circuits so that the efficiency becomes high, because these PMOS switches have higher efficiency or better performance compared to the lossy diodes. The losses in PMOS are almost negligible, and they can easily be synchronized. NMOS and PMOS can easily complement each other for smoother operation, for lossless operation, and so on. And controlling diode can be difficult, or it consumes more energy compared to PMOS. So that's why S2 is always designed using PMOS, switch S2. It can easily be controlled using this control algorithm inside the controller. Rest, all these components are there, but these, we assumed only this, like we assumed all these components as ideal components in previous analysis. But practically, inductance has its own resistance, which is R coil. Input capacitance also has its own resistance, electrostatic resistance, but we assumed all components as ideal, so we have not considered all these input parameters or all these internal parameters. Same over here, NMOS and PMOS, they have their own parasitic capacitors like this. And in previous circuits, we assumed all these to be zero. And at the same time, these NMOS and PMOS, they have their internal resistances, R PMOS and R NMOS, and parasitic capacitances, and so on. So all these NMOS, PMOS, and including this controller can be put or can be designed in VLSI on a single chip. So that's the beauty of NMOS and PMOS. That's why this PMOS is in industry or in practical purposes, this PMOS is preferred compared to D1. So what are the losses? Resistive losses we have I square R. Capacitive losses we have because all these switches, they have their own parasitic capacitances. So or input and output capacitances are already there. So due to these capacitances, we have some capacitance losses or capacitive losses, which are dependent upon the switching frequency, F, and the voltage applied in this circuit. So if we lower down the voltage, then the losses, capacitive losses, become lower. So depending upon these parameters and the value of capacitance also. Okay. So this is the inductor current. Continuous current we saw when we did analysis in previous slides. So a ramping up of the current and ramping down of the current and so on. So this is the net capacitor current. So these ramping up and ramping down of these currents are due to the capacitances present in the circuit and inductance present in the circuit, and also based on the switching frequency. So if the switching frequency is high, the ramping up and ramping down will become faster. So depending upon the frequency also. And similarly is the case for the voltage at the output to find out the ripples based on the capacitor. If you apply this output feedback before filtering, we can have a precise calculation by the controller. Okay, so before going into the practical aspects of the boost converter for discontinuous mode of conduction, let's go for one example. Design a boost converter having an output 30 volt and from a 12 volt. So the input voltage is 12 volts, output voltage is 30 volts. So we need to design this circuit for continuous conduction mode and having an output ripple voltage of less than 1%. So the load resistance is 50 ohms and switching frequency is 25 kilohertz. So I think better is to first find out the duty cycle. So the duty cycle comes out to be 0.6, 60%. And the minimum value of inductance using equation 7 as we did in previous slides, it comes out to be 96 microhenry. And now to provide a margin to ensure that current continuous mode of conduction is ensured, we need to assume the inductance is equal to 120 microhenry. So the inductor current comes out to be 1.5 amperes using equations 4, 5, and 6. So the change in inductor current is 1.2 amperes, again using equations 4, 5, and 6. So what is the maximum value of current? IL plus delta IL, as we saw in previous slides, which is 2.7 amperes. Minimum value of current is difference between IL and delta IL is 0.3 amperes. So capacitance has to be greater than or equal to that particular value over here we saw in equation, this one, which shows the relation between ripple and the value of capacitance. So ripple, value of ripple given is 1%, less than 1%. And resistance, the load given is 50 ohms and switching frequency given is 25 kilohertz. And we get the value of capacitance 48 microfarad for having a ripple less than 1%. So if we design this boost converter with capacitor value equal to 48 microfarad, we will have a ripple voltage at the output less than 1%. So this is when we assumed L greater than 96 microhenry. We saw that. This is the minimum value of inductance. So inductor has to be chosen above this 96 microhenry using equation 7, because this is the minimum value after calculation. So it has to be higher than this. So we have assumed 120 microhenry. So if we assume 100 microhenry, which is again above this minimum value, these values will change. IL will change, and all these values will change. Delta IL will change over here, because the inductor current remains fixed at 1.5 amperes. So this delta IL will change, and based on this delta IL change, we will have different maximum current and different minimum current. So based on that, if we assume if I minimum is 0, then this continuous inductor current we want to ensure is not there. So we cannot ensure a continuous inductor current if this I minimum is 0. We have already discussed in previous slides. For continuous current conduction mode, again I am repeating that the minimum value of inductor current must not be 0. It has always, or it should always be above 0. So discontinuous current, we already know the inductor current goes to 0. So this is one example. In this particular example, I've tried to show almost every detail that you have to ensure while designing this boost converter that it is running in continuous current conduction mode. And by using this inductor value, we can see that minimum value is still above 0 amperes. So this condition is okay. So we have fulfilled this condition that it is actually working in continuous conduction mode. And at the same time, the ripple at the output has to be less than 1%. Just by selecting this capacitive value equal to this or greater than this, so either 48 microhenry or greater than 48 microhenry, it will ensure that the ripple remains below 1%. Okay. So practical boost converter. Again, we have already done continuous current conduction mode in previous section when we did the complete mathematical analysis. Now we go for a discontinuous conduction mode for practical. And because in this particular section of this boost converter, I am discussing about discontinuous as well as the practical aspects. So no mathematical aspects in this case, because mathematical aspect is very simple. We can, based on this minimum value of inductance, you can decide whether to go for continuous or discontinuous, which can be proven by this value of I minimum. If I minimum goes to 0, then this condition of continuous conduction mode is disturbed. We do not have continuous conduction mode. So just by using these values, by selecting the actual or the required values of these parameters, we can decide whether this boost converter is running in continuous conduction or in discontinuous conduction mode. So mathematically, just by selecting these values, you can decide. But now, first we did qualitative analysis. Just by looking at the circuit, we can find out just by using electrical theory experience. Next, we did the mathematical analysis, complete mathematical derivation, and then how to decide the value of L minimum of inductance or coil minimum value of inductance or minimum value of current and all this, just using this mathematical analysis. Now the last part of this boost converter We have to just find out the practical aspects, that how to evaluate this boost converter practically. No mathematics, no qualitative analysis, only practical analysis. So this is the third aspect. So the same practical analysis can be used for discontinuous mode as well as continuous mode. So for continuous mode, as we did in buck converter, this phase 3 and phase 4 must be removed. So if we know discontinuous, we can just remove phase 3 and phase 4, we have a continuous mode. Straightforward. Okay, so just practical aspects. After this qualitative and mathematical analysis. Okay, so practically, this is the circuit. This is the inductance, a coil. It has its own internal resistance. This is the input supply, DC supply. It has its own resistance, internal. This is the parasitic capacitance. This is the switch, S1, which is NMOS, realized using NMOS. This is its internal resistance. This is the controller, analog or digital controller. So we are dealing with digital controller. And this is the feeding back of the output based on this current control and the standby control current. This is the output capacitor, a ripple capacitor, filter or a buffer capacitor. It has its own internal resistance, electrostatic resistance, internal resistance. And this is the load current. This is the PMOS switch, S2. Practically we use this so that the controller can easily synchronize the switching on and off of both of these switches alternatively, which are just used to remove the problems of synchronous nature so that they are mutually exclusive. Means they should not be switched on at the same time, even by accident also. So that's why this NMOS and PMOS, they complement each other synchronously, thereby increasing the efficiency, lowering down the losses, and improving the performance of this boost converter circuit, practical circuit. Okay, so phase 1, similar to the buck converter, 4 phases. So phase 1, this one denoted by phi 1 and the shaded area over here. The inductor current ramps up like this. And during this phase 1, this NMOS is switched on, as we saw in the case when we did the mathematical derivation. This NMOS switch is switched on or closed, and PMOS is switched off or opened. So in this case, in phase 1, the path followed by the current is through NMOS. Because PMOS is turned off, diode is reverse biased, so no path is given to the current to flow over here. So only this loop will be having the flow of current. So in this case, the coil current rises because the energy starts to store in this inductor or in this coil. Now, phase 2. In phase 2, this NMOS is now turned off or opened by this controller, and this PMOS is now turned on. This PMOS is now turned on, and now whatever energy is stored in this coil during phase 1 is now ready to flow through this PMOS switch, which is now turned on through this circuit. So when the current starts to flow from this stored energy in this inductor, which reverses its polarity when PMOS is switched on. So now the current starts to flow through this PMOS. It starts to charge this capacitor C out. As we saw in the previous slides. So now this energy is transferred from this inductive coil to the capacitor. So due to this transfer of the energy stored over here into this, the inductor current starts to decay, which can be shown here. In phase 2, the inductor current ramps down, because in phase 1, the inductor current ramps up. The energy is completely stored. We have a peak current over here. And now in phase 2, PMOS switch is turned on, and now the inductor current starts to flow over here. Energy starts to get released. The current starts to ramp down or decay. So due to this, the output voltage has a higher value, because now the energy released to this part of the circuit, to C out and load, is the sum of voltage across coil, inductive coil, plus the input voltage. It goes here, which is higher than because the node voltage over here, if assuming PMOS, losses in PMOS are very negligible, because in practice, this on-state resistance of MOSFET is very low. So the node voltage over here or node voltage over here is equivalent to the sum of the voltage across inductor plus sum of the voltage plus this voltage at the input. So the total voltage over here is the sum of both the voltages, which is higher than or almost double than the input voltage. So the voltage here at the output is greater than input voltage. Now phase 3. Phase 3, as we can see here with the shaded over here. Now the value of this decreasing coil actually goes to 0, because the complete energy stored in the inductor is now released completely, and the inductor current goes to 0, completely decayed, completely ramped down. So when it is completely goes to 0, the PMOS switch is now turned off or gets opened. So now both these switches are turned off. NMOS is turned off in phase 2, PMOS is turned off in phase 3. Now only diode is in the picture now. So the forward voltage drop over the diode is supplied by the coil. A very small energy remained inside the coil. So very, very small energy remained inside the coil from here till it reaches 0. At the end of till the end of phase 3, from the starting of phase 3, the diode, this PMOS switched off, and the diode takes over, and whatever energy remained inside this inductor is now transferred through this diode at the output till the coil current reaches 0 from this point to this point. Now in phase 4, the diode prevents the coil current from becoming negative, because there is no path through this reverse biased diode to have a reverse flow of current. PMOS is switched off, so the current will not follow this path. Diode is reverse biased, so no flow of current in the other direction. So the diode will prevent the flow of current through diode to the coil in negative direction. So it will maintain its zero value, which was at the end of the phase 3, the inductor coil, the current in inductor coil was completely decayed to zero through diode. And in phase 4, it never goes back because of the reverse biasing of the diode. So it remains at zero, never going negative. So it stops the energy transfer because now the coil is already fully de-energized. So no flow of energy in this circuit in phase 4. So the circuit will remain in this state where no energy will flow because this inductor is completely de-energized. So it will remain in de-energized form. So no flow of current during this phase 4 until the next cycle starts again, when we switch on the NMOS switch again to start phase 1, phi 1. So very simple. This is just a summary of phases of operation which I just described in the previous four slides. Then that in phase 1, NMOS is closed, means switched on, and PMOS is opened, and diode is reverse biased. We know that. Now in phase 2, NMOS is opened or switched off, and PMOS is closed, switched on. Diode is not having any function because the complete path is followed through the PMOS because it is closed now. In phase 3, NMOS is also off, PMOS is also off. Now whatever small energy remained inside coil, inductive coil, is transferred to the output through this diode we saw in phase 3. Now at the end of phase 3, this inductive coil is completely de-energized. So no flow of current will remain because it has decayed to zero. It has ramped down to zero. So in phase 4, PMOS is still off, NMOS is still off. Now diode is also off now. So now this circuit is in a standby mode. So consuming no energy. So standby mode. So practically this boost converter follows these 4 phases. And in our mathematical analysis of this boost converter, we dealt with the 2 phases, continuous conduction mode. So here we have already done 3 types of analysis: qualitative analysis, basic theory, no mathematics. Second one was pure mathematical analysis. So using mathematical derivations, we found out the relation between output voltage and input voltage, which have dependency on the duty cycle. And now the practical aspect. The third type of analysis was the practical aspect, where we have these synchronous switching as well as the 4 phases of operation in the practical boost converter. So now the next one is step up as well as step down, or in other words, buck and boost converter in a single circuit. So this is the buck portion of a converter. This is the boost portion of a converter. So buck portion of the converter will step down and boost portion will step up. So at this output, we can have a combination of buck and boost at the output. So you can easily see, or you can, I think, remember that this circuit was just a buck converter where we have high switch and a low switch when we did our buck converter analysis. And this boost converter has an input connected to the inductor, and then we have switches. In buck, we have switches first and then inductor. In boost, we have inductor first connected to the input and then switches. This was the NMOS switch over here, S3, and PMOS switch, S4. We just saw. So this is the practical circuit of a buck and boost converter combined together. So we quickly go through these practical aspects of the buck and boost converter. So up conversion first means the boost conversion first. PMOS 1 switch is closed. This one, this is switched on. PMOS 1 is switched on. NMOS 1 is switched off. So now these two remain in this particular position till we continue to have a step up at the output. So if we want to use this particular circuit, which has this portion of the circuit which shows a boost converter portion or up portion, and this PMOS 1 and NMOS 1 combined will give us the buck portion of the circuit of the converter. PMOS 2 and NMOS 2 combined will give us the boost portion of the converter. So if we want to configure the complete converter circuit into a boost conversion first, which is up conversion, PMOS 1 has to be switched on, and it will remain on till we continue using this circuit in boost conversion configuration. And NMOS has to be fixed to off position. So when PMOS is fixed to a on position over here, the circuit will follow this path. The voltage is connected to the coil now because PMOS 1 is switched on, and now the coil starts to get energized. And then the operation of boost converter will follow. So now this circuit input connected directly to the inductor through PMOS 1 because NMOS 1 is switched off through this one. So now this is a boost conversion or up conversion portion. So now it will work as a boost converter. And we can follow the same principle of operation for boost converter by first switching on the NMOS 1 for phase 1, and then for phase 2, PMOS 2 is switched on, and for phase 3, both are turned off. NMOS 2 and PMOS 2 are turned off. Only diode remains in the picture till the complete energy stored in the inductor is decayed to 0. And in phase 4, nothing happens, no transfer of energy, no flow of current. So the converter remains in the standby mode. So this is the usage of this buck and boost converter in a boost conversion mode. Now, the same circuit to be configured for the buck conversion mode or a down conversion mode, where we have a output step down compared to the input. So what to do over here? PMOS 2 switched. This switch is closed, and NMOS 2 switch is opened and fixed. So PMOS 2 is fixed, closed. It will not change until this circuit operates in buck conversion mode or a down conversion mode. And NMOS 2 has to be fixed for off position. And now we can see, we can use this buck portion as a buck converter by switching on this S high, which is PMOS 1, and S low alternatively in 4 phases. Phase 1, phase 2, and phase 3, and phase 4 for discontinuous mode. And if you want to have it only continuous current conduction mode, only phase 1 and phase 2 will be used. So just by fixing the switching off or switching on of any of these switches, we can configure this one circuit into two converter circuits. So for buck converter, PMOS2 is fixed on, NMOS2 is fixed off, and PMOS1 and NMOS1 are now operated in phases: phase 1, phase 2, phase 3, and phase 4. So if you want to find out the buck converter or down conversion configuration of this, you go to part 5b, where I have explained the operation of buck converter in detail. Okay, so now next one, multi-output, up or down or both, or in other words, buck or boost or both, having multiple outputs. In previous case, only one output was there, either boost output or buck output, based on the two modes, whether this particular circuit is required to be operated in up conversion mode, then we do these, then we follow these two steps. Or if the circuit is now operated in down conversion mode, then these two steps needs to be followed for one single output. Now, if you want to have multiple outputs like this, so this is a practical multi-output boost converter, means that we have two outputs, Vout1 and Vout2, output 1 and output 2. Both are boosted form of the input. So both outputs have a step up outputs compared to the input. So first phase, the controller opens the PMOS1 and PMOS2. PMOS1 and PMOS2, they are turned off. And only NMOS switch is turned on. Phase 1, as we just saw in boost converters phase 1, in phase 1, NMOS switch is switched on. In phase 2, PMOS switch is switched on. And then phase 3, both are turned off. And in phase 4, even diode is also turned off by reverse biasing. So phase 2. Now phase 2, we know that NMOS switch has to be opened or turned off, and PMOS switch has to be switched on or closed. But if we want to have only one output, let's say Vout1, we need to connect at the output, and Vout2 is not used, it remains open at the output. So the terminal, the wire is not connected to anything at the output. So let's say if only Vout1 is required at the output. So only PMOS1 has to be switched on in phase 2. And if we want to have two outputs, both Vout1 to be connected to some circuit, or Vout2 also is connected to other circuit, we want to use both the outputs. So then PMOS1 as well as PMOS2 has to be switched on for phase 2. And depending upon the values of Vout1 and Vout2, these values of Cout and the switching speed of PMOS1 and PMOS2 has to be decided. Phase 3, again the same thing. Both of these switches have to be turned off. PMOS and NMOS both have to be turned off. So if all the two outputs, Vout1 and Vout2, are used at the output, connected at the output, then both the PMOS1 and PMOS2 have to be switched off. And NMOS is also switched off. And now only diode takes the path, as we saw in the boost converter. So in phase 3, whatever energy, a small energy remained after phase 2 in this coil has to be transferred through this forward bias diode to the output. Now phase 4, a standby phase, a standby mode. So all the devices have to be switched off because there is no energy remained in the coil. Inductive coil is completely de-energized after phase 3. So nothing is there to be transferred at the output. So no current flows in the circuit. So it is a standby mode. NMOS, PMOS1, PMOS2 and diode, both all are off. So this is again the same thing. So diode is also reverse bias, means off in phase 4. Now, that was the case of a multiple output boost converter. Same concept can be applied for a multiple output buck converter over here. But if you want to have a combination of different outputs, means a combination of buck as well as boost, and at the same time multiple outputs. So this multiple output Vout1 and Vout2 can be used for step down as well as step up in the same circuit. So then we need switches that when this down configuration is connected to Vout1 or up conversion is connected to the Vout2 or vice versa. So let's say if we want to have a buck converter connected at the Vout1 and boost converter connected at the Vout2, both are used. This is used for a motor, let's say, and Vout1 is used for a speaker, let's say. So one is used, Vout1 gets connected to the step down or buck converter, and Vout2 gets connected to the boost converter using these switches. And then all 4 phases have to be operated as we did in the previous cases. And if we want to operate these converters in continuous mode where no standby phase is there, standby phase will save energy, save power, then only phase 1 and phase 2 will be applicable, where only NMOS and PMOS are in the picture. Okay, so with this, we come up to the end of these DC to DC converters.